Good. So, good evening again, and again, thanks for attending. So, this lecture will be complementary to our lectures on input interaction technologies like I guess tracking gesture or the speech recognition system. And this lecture will later be followed by another lecture on tracking technology, in which we will talk about various model view or projection transformations and tracking object for display. Within this display, we will look at the historical perspective of development of display, and then we'll look at a few types of AR and VR type of displays, and also you'll have a couple of slides on volumetric or 3D displays. So here is a brief history of display. So you can find the source from bottom. And if I will not go through all the rows of this table, but some highlights are in 1964, the first CRT display or cathode ray type of display was invented and started to be marketed as a computer monitor, even if it is invented a few years ago. And 1975, the first resistive touchscreen display was developed by George Hurst. Then jumping to 1997, Apple, IBM, and ViewSonic begin developing color LCD monitors that offer comparable or better quality and resolution compared to CRT monitors, and the overall size and weight of the display drastically changed. And in 2009, LED monitors for desktop computers began to be manufactured. And now we are living in a generation of OLED or even plasma TV display, which shows a much higher spatial and temporal resolution of display. So before going into various types of display, let us look at a very simple classification of display based on their relative position with respect to our body. So head mounted display system can be used for both augmented and virtual reality, and these are wearable device. And then we have the handheld devices like smartphone, tablet computers, which we hold by hand, and then I can use the camera to render outside field, and the outside live video feed can be augmented with uh, synthetic objects. And finally, we have the world space or the standard display, which we can say, and it can come in two forms. One is a stationary display like our computer monitors or TV sets, and the projected display like as we use during our class lecturing, that we project it on a screen. And the stationary display, they directly emit lights which reach our eyes. On the case of projected display, it reflects light on a surface and we see it through the projection. So this is a very early history of displays. On the left hand side, you can see the schematic of the CRT display and basic scheme diagram of liquid crystal display. So the CRT display has a cathode ray gun and it has RGB types of rays which combined, and it hits the RGB phosphors on the screen. And as the cathode ray gun hits the RGB phosphors, the different proportion of mixing of the red, green, and blue colors create the gamut of color vision. But most CRT displays do not uh, display the whole gamut of human color vision. In case of LCD display, mostly there is a backlight and it illuminates a set of liquid crystals, and there is a polarizer in front of them, and based on the by tuning the voltage difference, we can create different shades of gray or different shades of light through the LCD. So the LCD itself doesn't emit light, rather the backlight is polarized through the LCD or the liquid crystals, and that creates the display. And when the backlight use the standard CCFL or cold cathode ray, so that becomes the standard LCD display. While when the LCD display use the LED backlight. So we popularly call it a LED display, but the LED display is that LCD display which is backlit by LED. So that is the standard LED display. And now we also have OLED or organic LED display. So in standard LCD, we have backlight through the CCFL or cold cathode fluorescent light technology. In standard LED, we have LED backlight, and in organic OLED, we have with the LEDs, they directly emits RGB type of light, and that mix together. So it doesn't use another backlight, and the advantage is it has a wider color gamut than and a wider dimming range compared to standard LED or LCD display, and of course greater contrast ratio, and very slim, but also has an advantage in terms of also has an disadvantage in terms of recycling. So this is a picture of comparing contrast between the LCD and LED monitor, although the picture is not rendered very well in this screen, or you can may not see it very well. But the LED and later the OLED has a better contrast ratio, dimming range, and bigger color gamut display capacity than the CRT or liquid crystal display. So at this point, it will be interesting to note that how we characterize displays. So there are several properties by which we can characterize display. So already we talked about two characteristics, that are wider gamut of color vision and bigger dimming range or higher contrast ratio. But inside of that, there are some other properties also which we can look at display. If we look at a wider range of display consisting of both head mounted display or handheld display and so on. So some of these properties are like the stereoscopy. That means we when we can perceive depth by creating two slightly different image in each eye, and our brain can process this different information, these different images, and that's we can perceive depth. So in this slide, VST stands for video see-through display, and OST stands for optical see-through display. So when we use two different video source, so that we can perceive or we can render depth easily, and that is the stereoscopy display. Similarly, the focus of the display, that there is a challenge in augmented reality type of display, that is called accommodation divergence conflict, which means that when we are looking at the augmented reality type of display, in one side we are looking at the real objects, and we have no control on the z-axis or the depth of the real objects that is captured by the camera. On the other hand, we are creating some synthetic objects on top of the real object, and that may occur at a, or that usually occur at a different z-axis or different depth than the original object. More interestingly, that the real life object may be a moving object, so constantly its depth is changing with respect to the viewer, but the synthetic object is created at a fixed z-axis, and this problem known as accommodation divergence conflict in the context of AR display. A few solution of this problem, and the problem becomes significant for the human viewer, that when he wants to focus on the synthetic objects, he has to focus on a particular z-axis, but that may cause him to lose focus on the faraway object. You can think the problem more seriously from the driving point of view. Say I am using a head-up display which is projecting objects at the plane of the windscreen. So when we are looking at them, I am not focusing on the faraway traffic participant which is maybe moving towards me, and vice versa, that when I am looking at the faraway road, I am not focusing on the head-up display. So some way of solving is using eye gaze tracking, that where finding where the user is focusing and creating the synthetic object at that plane only, or constantly sensing the depth of real life objects and adjusting the synthetic objects accordingly, which is very much computation sensitive and so on. Then occlusion is another property of mostly virtual reality display, that where virtual and also partly augmented reality display, that where virtual and real objects, they can occlude each other, and the resolution, which is often constrained by camera resolution in case of video see-through display, a refresh rate, that how quickly it is changing, and if the refresh rate is low, then flicker may offer field of view and of the display. And for augmented reality display, the field of view is restricted by the camera, which is showing the real world object. And also in a virtual reality system, the field of view comes into picture when we are moving our head. We want to update the screen synchronously like real live. So even though we have a smaller FOV, but we have to create the virtual scene for a bigger FOV than my static head position. And then there are other properties like viewpoint offset, which requires calibration for video see-through interface. We will see the video see-through interface in a few slides after. And the brightness and contrast, which we already discussed, and also considering outdoor contrast when we talk about augmented reality display, distortion, ergonomics of the display, like a bulky headset like the Microsoft HoloLens or a HTC 5 set. Those are fine for a short duration study or demonstration, but if you want to wear it all the time in a factory floor, that then it becomes unrealistic. On the other hand, lightweight wearable may be a possibility, or even if we have a display which is a handheld device, then that becomes more ergonomically easier to handle. But then every display has its own limitations. So moving on, this is a classification of see-through displays, or mostly the augmented reality types of display, and the broad classification is based on the stereoscopy, that means monocular or binocular. And then both of these um, types of display can be divided into video see-through and optical see-through display. And for video see-through display, we can further classify based on the number of cameras. And in case of optical see-through display, we can look at the overlays, that means the layer of the virtual object on the real life object. So let us look at what is this optical and video see-through display. So this is the very simple arrangement of optical see-through display, that the real world is coming from right hand side, and we have an optical combiner, and then we are generating virtual annotations on the optical combiner, and the user, he is looking at the real world, but he is also seeing the virtually generated object. And ideally it should also has a post sensor of head movement, so wherever the user is looking, the display should move synchronously with his head. So this is probably we already went through this video. So this is one of our laboratory work on creating optical see-through display. So here the windscreen itself is acting as a optical combiner, and TFT or a high brightness tablet, in this case the Microsoft Surface Pro tablet, which has a high brightness level, that is acting as a image source. So we are rendering these icons on the real world scene, and through the eye gaze tracker, we are tracking the pose of the head, and we can detect whether the person is looking straight ahead or whether he is looking away, in which case we are sounding an alarm based on the distraction of the person. So here you can see the video see-through feature further, that these icons are overlaid on the actual screen. So in comparison to optical see-through display, the other one is video see-through display. in case of optical see-through display, the real life objects, those are combined with virtual objects using optical combiner, but you are still seeing the real life objects. But in several situations, we capture the real life using a camera, and then we combine it with virtual objects. So that type of display is called a video see-through interface, where we have two cameras, or maybe we are using or we can also make it with one camera if we have a different way of uh, sensing pose of human. So that we use a back-facing camera. Back-facing means that it is looking the other way than the user. Here, this is termed as image sensor, which is sensing the real life. And in the digital combiner, we are combining the real life video with virtually created object. So this is again another example. We have looked it in some earlier lecture of video see-through interface, in which we users are interacting with eye tracking for a human robot interactions task. That the red blob is showing the eye gaze location, and the real life is rendered through this video screen. And then users are operating the real robotic arm looking through the live video feed. And then we can render. So in this screen, we do not render anything, just we are sensing the eye gaze. But we also have, in this application, we also have object recognition feature. So since we are sensing the outside environment through a sensor, so we can process the sensor information for a desired type of target. So in this case, we are tracking this blue cap. And similarly, we can track any other object or any specific anything with a specific shape or color signature. We can track through the video see-through interface, and we can render the virtual objects, in this case a set of icons, accordingly or based on the relative position of the real life object. And then we can add interaction layer, in which we are, in this case, we are using eye tracking, but it need not to be eye tracking. We can also use other modalities like traditional touch screen, touchpad, or gesture recognition, speech recognition, or whatever. So moving forward, the third type of display is the projected display, in which case we project something on real life objects, and this projection add extra information. So for example, here, this is another demonstration from our laboratory. So we were trying to make a sensor dashboard which is showing both spatial and temporal information together. So here what is happening, that the screen uh, of, uh, right option top of that on the screen. So this is a kind of early stage research example, but we can also project information on real life objects. Like you may note that nowadays it's pretty popular that uh, the branding advertisement is projected on the floor or the shop floor. So it can be very naive that it's just projection, or it can be more objects. The pupil will contract or dilate based on the ambient light, but we have to adjust the brightness of virtual object based on the real life illumination condition, and combining wide field of view with small lightweight form factor. That means showing up um, or annotating a wider range of real live video with augmentation, but with a smaller form factor of display. That becomes challenging. So for a VR headset, the whole display or the whole display principal is packed inside the glass, that we will see in a few slides after. But in a AR type of display, the size of display is pretty small, and it becomes challenging to uh, take care of the wider field of view of natural display. So just to mention one more time that in the next semester, when we will run this AR VR course, so we will have some hands-on session on teaching AR and VR programming with Unity. So if any of you are interested, you can continue with that course. But now let us move on to other types of display. So from the augmented reality, let us move to the virtual reality type of display. And here the situation is slightly different. That means that we create a uh, or we integrate the display inside the headset, or we can also use a projection system, and the user has to wear a specialized polarized glass to
Sorry to interrupt. If you're speaking, there is no sound here.
anyway, I will continue with the lecture, and I can see a bad network quality notice. But anyway, I hope this is being recorded, and I will share the recording with you. So let us continue, and then I will If required, we will come back and I will run this final set of slides once more. So this is a picture of a holographic display, and the left-hand side picture is taken from a recent worldwide patent where a holographic display has been proposed to for a automotive user interface use case, and it utilizes the diffraction of light to create a virtual three-dimension image or object. And in fact, there is a whole museum in Crete on holographic display. And these are distinguished from other forms of 3D imaging is that they do not require any glasses or any wearable to view, and you can look it like a real life objects. Although holographic display with a high enough refresh rate is not still commercially available. Rather, most holographic displays those create kind of static displays, but the static displays they are very the resolution is as high as a real life object, so it's almost indistinguishable from a real life object. The other type of 3D display is again it's very much in the research stage, is a volumetric display which can display object in 3 dimensions. And here also you can see that like a um, holographic display, the user doesn't need any wearable. So one example is Voxon Photonics and autostereoscopic display, which are autostereoscopy is the term which means that for stereoscopy you do not need any extra wearable, and it's automatically create stereoscopic display. So a very early example was created in early 1990s at Cambridge University computer lab, and it's still there. And presently the autostereoscopic display holography is one such example. And this Voxon Photonics, they are creating such a display. And the Ultra Leap, uh, which recently acquired the Leap Motion company, they are also creating a type of volumetric display using ultrasounds. But the issue is same, that the refresh rate is not good enough for a real life application, but still research is going on to increase the refresh rate so that we can render any graphics on that, and we can change the graphics in real time. So presently we can render any graphics on volumetric displays like holography, or maybe using these ultra leap sensors, but the refresh rate is not big enough for changing the display in real time. So the main take-home points are the history of display development and different types of AR/VR-related displays. And most of the discussion was at the introductory level, but we can go into further depth in for each type of display when we'll talk about tracking, calibration, and transformations. And we also talked about classification and main characteristics of display and some futuristic work on the autostereoscopic and volumetric display. So with that, I will stop talking. And sorry if you do not hear any part of the display, any part of the lecture. So now I will stop sharing and recording, and we can look back.
Earth has a diameter of roughly 8,000 miles or 13,000 kilometers and is round because gravity pulls matter into a ball. But it's not perfectly round. Earth is really an oblate spheroid because its spin causes it to be squashed at its poles and swollen at the equator. The moon was created when a rock the size of Mars slammed into Earth, shortly after the solar system began forming about 4.5 billion years ago.
You are facing an entry point to an abandoned settlement. All around the town is a wooden fence. A wooden path leading down to the sea. On both sides of the path are wooden buildings. Studio available. Entrance to the smithy. Another exit to the left. Scan start. Stack of buckets. Pillar. Plank pile. Skull stick. Smithy wall. Halfway point in smithy.
Sword.
Sword. Pillar. Reached sword. Press Y
Sword.
to pick up.
We investigate the possibilities of using synthetic data to train and validate CNN models. By utilizing PBR materials and baked global illumination, we constructed a digital twin of a workspace. We chose YOLO version 3 as our person detection model, and we computed the bounding boxes and the corresponding centroids. We then calculated the Euclidean distances between these bounding boxes. If any two individuals were to come within the 6 feet, the otherwise green bubble